Okay, so this is the 7th video in electromagnetism. This video we are going to be covering magnetic fields, both the things that create them and the effects of various magnetic fields. So we're basically going to go through that whole point D. All right, so the source of a magnetic field is basically, actually we're going to start not with the source of a magnetic field, but the effects of a magnetic field. And the effects of a magnetic field on a charged particle. If you have a charged particle that is placed in a magnetic field, first let me define a magnetic field. Magnetic field lines always run from the north end of a bar magnet like this around toward the south end. I feel like it should go towards the north. No, that's correct. From the north magnetic pole. Here we go. And we know that electric forces, the force in electricity is equal to Q times the electric field, whereas with magnetic force, it's going to only act on an object when it is moving. There will be no force of magnetism placed on a charged particle, even if it's stationary, only if it's moving. So actually, this is a really good. There it is. The force of magnetism on a charged particle is Q times the velocity of that object times the magnetic field strength, which is this B, times the sine of theta. In other words, they need to be perpendicular to each other. So let's go back to those rules. For the electric field force, these are the similarities between the electric force and the magnetic force. Magnetic and electric force are proportional to the charge. Magnetic and electric is on a negative charge is directed in the opposite direction of a positive charge, so it's directional, it's still a force, so it's a vector. And the magnetic force is proportional to the magnitude of the magnetic field, just like it was proportional to the magnitude of the electric field. The differences are that magnetic force will not act unless the object is moving, unless the charged particle is moving. And it has to be moving with some component of its motion perpendicular to the magnetic field. If it's all parallel, the magnetic force is 0. So again, here's the formula, QV cross B, or QV sine theta, and you do need to know the right-hand rule. For the right-hand rule to determine the direction of the electric force, your thumb will be the direction of the velocity of the object. The magnetic field lines are your fingers, just like field lines are always kind of drawn like that for a uniform field. And then the force experienced by that charged particle that's moving is, and if it's positive, it would be, the palm of your hand. If you were talking about an electron, the force experienced by an electron that's moving along your thumb's path with a magnetic field going this way would be the opposite direction. It would be back out through the top of the hand. Moving to the next stuff. The unit of magnetic field is a Tesla. Let's see, we're going to come back to that. I don't think I defined that yet, but a Tesla is a Newton per ammeter. It's probably in the last slide. You do need to know that. The unit of magnetic field is a Tesla. And then if an object is moving and it enters a magnetic field perpendicular, if it enters this magnetic field going straight this way, or this magnetic field is coming out of the page, and let's say it's a proton is moving this direction from left to right across the page, then it would experience a force, if you're going to use the right-hand rule, that would be entirely downward. And that would be it would cause circular motion. It would cause this thing to always circle here. Or if it was here, it would be the opposite direction of circling. Again, use the right-hand rule. Here's a diagram of that. If, however, a charged particle enters magnetic field with some portion of its velocity perpendicular and some portion parallel, well, the parallel portion will keep it moving in this direction along the path of the magnetic field. But the perpendicular portion will cause it to circle as well, so that creates a helical path there. All right, some of these applications, and you do need to know that the Lorentz force is the combination of the electric force and the magnetic force. This is the electric force right there, well, those first two pieces. This is the electric force, and this whole thing is the magnetic force. And those two forces will not be in the same direction. Often they are in opposite directions. When you rearrange that, you get the velocity of something is the electric field divided by the magnetic field. And so we can use this for a number of applications, the first of which is a velocity selector. If you place a charge going through this direction, completely perpendicular to this magnetic field, if it has just this velocity, which is the ratio of the electric to the magnetic field, then these two forces will cancel. Your net force will be 0 in the horizontal direction, so it will continue straight. If it were going too slowly, the electric field would be greater, and so it would veer this direction. If it were going too quickly, the magnetic field, would cause it to veer to the left. Another application of the Lorentz force, which is the combination of the electric and magnetic forces, would be the mass spectrometer, where you place a charged particle, it goes through a velocity selector, and then it goes through a uniform magnetic field, and so the mass of that object causes it to turn with a particular radius. And you can kind of look at these equations, but basically mv squared over r is equal to, mv squared over r, which is the centripetal force, is equal to qv cross b, the magnetic force. And when that's rearranged, you get this. But if you can just get that it's a centripetal force that's causing it to turn, and that is equal to the magnetic force, which is qv cross b, then you can rearrange it. And then the final application is a cyclotron, which would speed up the object dramatically. Again, you keep adding kinetic energy here, and so that's a function of the magnetic field and the radius and the mass of the object as well. I'm not too worried that you know all of those applications, but kind of be familiar with them slightly. All right, the next topic, so that's how you measure the magnetic force on a charged particle or a moving charged particle. It does have to be moving again for it to have a magnetic force. But then we get to a magnetic force and how it acts on a current-carrying wire. And for a current-carrying wire is just a lot of charged particles that are all moving in one direction. So you're going to use the same right-hand rule that you were using, where your thumb is going to be along the path of the current. Your fingertips would be along the path of the magnetic field. So here your thumb would be going straight up, and your fingertips would be going into the page. And this current-carrying wire would experience a force that would be to the left, which would cause it to displace this direction. If, again, you're using the current-carrying wire in the same right-hand rule, but the current's going downward, so your thumb is downward, the magnetic field is into the page, so the palm of my hand is going to the right, and so that's why it's deflected to the right. Experiences a force that direction. If you have a number of different wires, so what was QV cross B has now become IL cross B. I being the current, L being the length of the wire itself. And both of those are on your formula sheet, but it's basically the same concept there. And there is a calculus form in case this wire turns. It's I integral ds, and that's ds cross B. You only want the portions that are perpendicular to the magnetic field there. And we'll go through and do that example. Torque on a current loop. So if you have a loop that's carrying current, the torque here, there's no force from this because it's parallel to the magnetic field. There's no force from section 3 because it's parallel to the magnetic field. But the force for section 2 would be directed, out of the page, and the force from section 4 would be directed into the page, so those would cause it to rotate. You would get a net torque acting on this. Here we go. This is showing it from above. So it's line 2. Did I get those backwards? Oh no, they just have it drawn differently. 2 is going into the page. Yeah, so it would be directed out of the page and into the page. But in other words, opposite directions. So a net torque is established. And that torque is when it's completely perpendicular. I'm sorry. Yeah, when the magnetic field is parallel to this. In other words, the area is parallel to the magnetic field lines. Then you get IAB. That's the maximum. If this thing is turned so that this theta is 90 degrees, then it experiences no torque, but it probably has some momentum which keeps it rotating. So that's where you're getting IA cross B. Again, the ones with the greatest net force, or which ones experience the greatest torque. One with the greatest torque would be this one, C. Then B has a little bit, and A has 0, because these two cancel each other out. That's what it's saying. I'm going to come back to the Hall effect. Not sure, but the Hall effect is just the separation of voltage across something that's carrying current because of it's basically a velocity selector, but it moves like this. Looks like a velocity selector. Y'all see that? But it causes the charges to move that way or that way, depending on if they're positive or negative. This is that IA. Again, this is for current carrying wire. That was for a mass spectrometer, current carrying wire, loop. Again, current carrying wire, it's just the calculus version. Oh, and the potential energy is negative mu, which is IA, dot B. It has to be parallel. So this should all be, there we go, Tesla right-hand rule. And actually, I think I'll do the second half of magnetism in just a second.